Now here is another question based on the application of differential equations to geometrical problems. In an inverted cone of height 9 cm and base radius 5 cm, water is being poured such that the rate of water level rise is pi upon A centimeter per second, where A is the area of the water surface at that instant. When will the cone be full? Now here, if we take the look at this particular problem, let us first draw the figure so that we get an idea of the different parts of this problem. There is an inverted cone, so let us draw a cone in which the water is poured, right? So here is the axis of the cone. Now, as the water is poured, clearly it will form a circular top surface, isn't it, as the water is poured. It's given that the base radius of the conical container is 5 and the height of that cone is 9. The total height is 9 centimeters. Now the area of this particular water surface at any instant is given to be A. That's the symbol A. Let's denote the height at any instant as h and the radius at any instant as r. Now let's try to write in all of these problems involving geometrical quantities, we have to write the given data in terms of symbols first. So it's given that water is being poured such that the rate of water level rise. Now you see, rate means the derivative, and since it's the water level that is rising, that means it is the height of the water column that is rising. So therefore here we have dH upon dt equal to pi upon E. Now we can write A, that is the area of the top circular surface of the water, as nothing but pi r square. So cancelling pi, we have 1 upon r square. Now the question says that when will the cone be full? That means when the height of the water column will become the complete 9 centimeter. Right? That means we must get height as a function of time, but you see height is continuously changing as the time moves ahead. That means we must get an equation involving h and t only, right? But if you observe whatever we have got an equation, rather it's a differential equation, as we can see, that involves h, t and r. And you see r is also a variable because as the height of the water column rises, its radius will also increase. So somehow we must eliminate or replace r in terms of h, because we don't want 3 variables, we want only 2, h and t. So let's ask the question, how can we eliminate r? For that, let us look at the given data. That is, if you see, we are given the base radius and the total height, and at any instant if we visualize the vertical cross section of this particular cone, you will see that 5 is the total base radius and 9 is the total height. If r is the radius at that instant and h is the height at that instant, clearly from the similarity of triangles we know that r is to 5 will be same as h is to 9, correct? So that's the clear ratio in r and h. So with the help of that ratio we can easily replace r in terms of h. And so we write as r upon 5 is equal to h upon 9. Therefore we have r is equal to 5h upon 9. Okay. So therefore here we get 1 upon r square is nothing but 5h upon 9 the whole square. So that becomes 25h square into 81. So we can just write it as 81 upon 25h square. So therefore we have got dH by dt to be equal to 81 upon 25h square. Clearly this is a differential equation of the type variable separable, right? So let us write it again. dH by dt is equal to 81 upon 25h square. So collecting all the h terms on one side, we have h square dh is equal to 81 by 25 dt, and hence on integrating we will get h cube upon 3 is equal to 81 upon 25 times t plus c, isn't it? Now to get the value of this arbitrary constant c, we use the boundary conditions. We know that in the beginning, that is when t is 0, there was no water in the cone. That means the height of the water column is nothing but 0. So when we put h as 0 and t as 0 in the above equation, we get clearly value of c to be equal to nothing but 0. So therefore we have h cube upon 3 is equal to 81 upon 25 into t. Now let's come to the actual question. They are asking us when will the cone be full. That means we have to find out what will be the value of t when h becomes equal to 9. So therefore we have 9 cube upon 3 is equal to 81 upon 25 times t. This is very straightforward, we can easily solve this, and we will get the value of t at the end as 75. Of course the unit is seconds, so that means the cone will get full in 75 seconds.